getting it better started. So you're in this Pathfinder Challenge for Nanoelectronics for energy efficient smart edge devices. Thank you for being here. I want to make it really interactive, so I would be glad to receive your comments, even if you want to stop me at some point. But else, I'll give the presentation. It's just like 19 slides, but I'll go pretty fast, and then you can just ask your questions. And we just have, I want to make sure we just had one pitch, someone from CNRS. Yes. But maybe if someone else wants we're okay also. If someone wants to pitch even without slides, maybe we can do this more interactive. It's a very small group, so yeah, glad to see your presentations later. So what's this topic about? So yeah, of course, all of you know that this energy demand of microelectronics is really accelerating now. So many examples about machine learning, AI really doubling the energy consumption every 2-3 months, all these non-computing communication applications that are now becoming computing, and also the electrification. So everything is expected to really increase the energy use and the consumption of energy demand. And this trajectory is expected to increase in such a way that we need to really do something. So you can see that the expected increase in energy consumed by supercomputers measuring in this giga floating point operation, so gigaflops per watt, expected for 2040, it's really a trajectory that we cannot bear as a planet, let's say. So if we deep dive a little bit more into the energy consumed per operation, both at system level but also at the transistor level, you can also see that the developments are slightly helping in this decrease. So the new developments are helping in decreasing the energy consumption per device. But still, there are many things that are happening. Like, for example, this energy efficiency increase is really now slowing down based on miniaturization. Up to now, it was really, we go down in miniature in the nodes, and then we achieve really energy consumption reduction, which are very good. But now this is changing. So this is changing on one side because time between successive technology nodes are extending. So this is also happening. This miniaturization also, there are many called leakages. And also it's very important to mention all the thermal management issues related to especially to the sub 10 nanometer node chips. So all these results in an energy efficiency scaling, which is not keeping the pace that was expected and to be doubling every two years, this efficiency. So it's doing it every 3 years, and this is a huge problem. And when we think of the great increase that I just mentioned in the use of new devices, we really need to tackle this. And this is basically what this challenge is about. I'm showing also the information of what's happening in the interconnect power as a percentage of the total chips. You can see that depending on the node, the technology node, the increase there of the power at the interconnect is really huge. So those are the things that we would like to tackle in a Pathfinder. So really disruptive innovation. We are not talking about doing slight changes in the devices, really trying to tackle really disruptive innovation. So the scope of the challenge is what reads here. So the overall goal of the challenge is to explore novel materials and beyond CMOS devices, non-von-Neumann architectures, and alternative information processing paradigms to drastically reduce energy consumption in order to meet application-specific needs of smart edge devices and circuits. Why smart edge devices and circuits? Well, you can see there the edge computing market is going to increase by 30% in a period of 10 years, so really huge. And the problem of temperature thermal management is especially relevant in smart edge devices. So, well, also again, smart edge devices will be used everywhere in consumer, but also in industrial application. So this is very important, and the fact of the energy consumption is even more important in the edge devices. So that's why this topic is about edge devices. It's not about data centers. It's really about bringing everything to the edge. And I think it's important to mention so drastic reduction of the energy consumption, and we also want to do it to meet the application specific needs. So it's not just we do it per se, but we want to meet the applications of whatever smart edge you will see later that several of them are mentioned. So the specific objectives of this challenge are very much in line with the international roadmap, the IRDS, that most of you probably know. So the proposals are expected to address the following aspects. So the fundamental issues like heat dissipation at the nanoscale, covering the design of the devices. So really from the understanding of the physics and the nanoscale thermal transport at component level, we really need to select the materials, the process solutions, physics behind the design of the devices. But we also want to demonstrate the potential of this developed technology for the energy service, for the environmental footprint towards responsible smart edge device. So those are the specific objectives, which translate in a series of examples. Those are examples, so this is not exhaustive list of what things can be done, but some example at a different level. So developments at design, device, and architecture level are mentioned in the topic. So at design level, we're expecting to see a lot of computer modeling. So again, fundamental understanding of heat transport, what's happening in the interfaces, how can we harvest these fluctuations instead of fighting against them. So everything related to all those different state variables, phonons, of course. So really computer modeling of this basic fundamental physics is very important, will be very important. Also the analysis of the dissipation mechanisms, so especially in signal transmission and conversion, heat removal. So really the understanding of the physics and the design based on computer modeling is something which is important. I'm showing some articles just for to try to illustrate what I mean by this. So, for example, we have a design at the nanoscale of the heat transport. We have ab initio calculations, and we have this thermal modeling of hybrid three-dimensional integrated photonic electronics transceivers. So those are different scales. So not everything is going to need to be done at the ab initio calculation. It can also be done at thermal modeling. And we want to put all those things together at the end of the day, and you will see that in the portfolio management also. Examples, This is not exactly what we are expecting, but those are examples. Then there's a big topic around materials and processes. Again, some examples. Of course, interconnections are very important. Switching mechanisms, I already shown all the energy that is spent on those, especially when you go to the smaller nodes. But we are also looking into the use of 2D materials and other novel materials for example, in-chip heat dissipation. Again, those are all examples, or you don't need to stick to those. But I put some articles down there. The use of phonons, the use of 2D materials to really go into sub-picowatt computing, novel nanocomposite superlattices for low energy, high stability. Examples. Phase change memory. This is a specific device. So those are examples of things that can be in there, just for your understanding of what's expected. Other examples are embedding energy harvesters in the final device or the circuit. Afterwards, I will try to explain a little bit what's circuit, what's a device, what's architecture, because, well, I know that, the semantics are important at this point, and it's not very clear. We use very different words, so I'll try to explain this. And also, I think it's very relevant if we come with some 3D multi-die heterogeneous integration novelties at packaging level, novel materials, novel ways of integrating modular designs, all these things related to chiplets, but in the context of really reducing the energy consumption of the final device, the final circuit that we are building. Okay. Then we have this. Maybe I should have had it before. So I'm taking again the IEEE under the IRDS, let's say, way of understanding what a device / circuit is, what system / architecture is. So those again, don't stick to those, but let's say that a device, memristors are devices, oscillators are devices. I showed that the CNRS presentation. So those are really the device level. And I would like to see proposals at that level, not so many at the architecture level. Even if it's mentioned, I want you to know that we have many projects at architecture level already in the open of our Pathfinder. So one would be okay, but you will see in the challenge guide that we are going to select just one on the architecture. Architecture meaning inspired systems, or these reservoir computing. We have several projects also on our portfolio of the open. So this is a little bit how I try to differentiate between devices / architecture. So not just a transistor, but a transistor together with several things to have an oscillator, or more at the architecture level. Afterwards, maybe I can explain myself better, but maybe keep it in mind now. So when we talk about, again, this at device architecture level, we can see molecular electronic circuits. We can see all beyond CMOS kind of solutions that we are seeing now. So really non-mainstream semiconductor transistors. So this is also very relevant here. More examples of the things that we're expecting to see. And just at architecture level, I would like to see just one on alternative processing approaches, non-von Neumann architecture. So again, as I said, we have many, and you can work on that, but we are not expected to be funding so many on this architectural part. Even if it's super relevant for energy efficiency, don't get me wrong, but we have so many projects now running that we want to put the focus more on the device circuit level. And then what's the expected outcome on the impact? So the portfolios are expected to collectively work on the fundamental bounds of energy consumption and designing practical and basic scenarios to really minimize the energy cost of the different processes. And also to harness energy efficiencies and optimization tool to operate these smart technological choices to build the smart edge devices. So we want to understand the fundamentals of the energy consumption, and we also want to have some kind of metrics optimization tool that we can afterwards be used to select and to build these smart edge devices based on building blocks somehow. Okay, so again, this is an unprecedented way we were looking for unprecedented ways to reduce the power consumption in information processes, in transmitting, by developing these new fundamental technology solutions, going from advanced materials, advanced devices and circuits, and holistically allow a drastic reduction of energy consumption. I'll come back to this picture with all these different materials, architectures, because also it has to do with the challenge guide, the way it's written. Please make sure that the challenge guide is not exactly written exactly the same as the topic. You will see that we have slightly different wordings and slightly different ways of selecting the projects. I will go through those a little bit later in my next slides. So what would we want with the projects that will be selected? Of course, we want close collaboration, and we want to promote a lot of interactions. And we not only want to work on the technology, which is very important, and that's the part that we feel that you find easier to collaborate in technology because you are used to that. But in this case, it's going to be very important to collaborate in these metrics. So let's try to find ways of putting together all the energy consumption metrics and to do it in a very holistic approach. So we have metrics for transistors, we have metrics for specific thermal management, but let's try to put it together and what the influence of each part of a final device, how do we build all this, okay? Other kind of things that we do with the portfolio, I think you already saw some examples. So we do a lot of common communication, of public awareness, which we try to put in contact also with investors. We do a lot of things related to communication, dissemination, and of course, exploitation routes. So we try to find novel exploitation routes, which is not written here, but it's very important also. Like, for example, in another portfolio that I'm managing, the one on DNA storage, we have 4 working groups, just an example. We have a working group on technology collaboration. We have another working group on communication and outreach events. we have another one on metrics, because in that case also it's very important, and metrics as a foundation for standards. And then we have another one for protection, so IP and exploitation. I envisage something very similar here. So again, 4 working groups probably in those 4 topics, okay? And then this is how the portfolio will be built. So this is how the challenge guide reads. So initially, I'm going to read what it says, because initially the evaluation committee will look at different proposals under the level category. So categories are this. This is what I meant, that it's not exactly written the same way as the topic. So we have 4 categories. We have one category which is called novel nanoelectronic solutions. So there, anything related to 2D materials, to really going into the nanoelectronic solution will be there. Another category is circuit level, understood at device/circuit level. So embedding energy harvesters, working on integration of analog, digital, optical. So really device/circuit in that case. Another big topic will be advanced packaging technology. So all these 3D integration things that I was mentioning, new interconnection, it can be optical, but it needn't be. So novel switching mechanisms. And then, as I said, architecture level solutions. So I really wanted to differentiate the architecture here. So how will the composition will be? First, we will categorize one of those 4. And it will be mainly I know that you will be touching upon several of them, but the category will be, where is your disruption really? Is your disruption at the materials level in the packaging, or is your disruption on the use of graphene for whatever in chip heat dissipation? So that will be the first categorization that the panel will be doing. And then based on that, we will try to look for, I'm going to read because I don't want to make a mistake. So the first 3 level values will different, and then we would like to cover the different application category. So we will first select one project per level category, so one of the 4, and then we will try to find the next one. When we go for the, let's say, the 5th project that we will be selecting, it will be in a different application to the one that was selected, the first, the 4th, the 2nd, the 3rd, or the 4th. Is it not very clear maybe, but so the idea is that we find all the 4 level categories, but at the same time, we also see different applications. So communication, processing, power management, sensing. We want to see that so that we can build also complementarities at the application level. Okay. So what else do I have here? Okay. I think with that, this is really the wrap up a little bit of what we're expecting. So the objective is really looking into the combination of solutions at the different levels to support the objectives, the scope. So really, again, drastic impact on decreasing the energy consumption of any smart edge device. And also to explore the use of this energy efficiency as an additional design variable, and even try to put it inside the software kind of technologies also. And of course, in-depth understanding of the physics, and also experimental demonstration should be there. But well, I leave it to you to read the topic in detail, but experimental demonstration is also important here. So you should not stay at the understanding of the physics level. You really need to demonstrate that you are doing something in terms of energy efficiency. So combination of solutions at the different levels, the 4 levels we want to build, and also to see some different applications where we can tackle this. And finally, some examples of what we are expecting. So of the portfolio activities that we could be doing. So at technology level, providing access to specific research infrastructure, design tools, specifically now that we have this chief joint undertaking new instruments. So we can do this liaison with the chip joint undertaking if needed, with the novel design platforms and design tools that will be available. I would also like to design scenarios to minimize the energy consumption. So this, I think, would be a good way to start collaborating Also, this exploring how to infuse this co-design process in the as I was saying, in the EDA or software EDA tool chain. So how can we really from the design level integrate these metrics on energy consumption? So those are examples again. So you can imagine others, and you can put them on your portfolio activities also. But those I already see that that could be very interesting. All those other good set of activities will also go in this exploitation and transition of the technology to innovation. So we are doing a lot of mapping common targeted players, for example, exchange of the market research analysis. Many of you will have this market research analysis in your work packages. So we are sharing those and seeing if we can have an impact and building a common understanding of who are your targeted players. And of course, also putting you in contact with those targeted players. Sometimes they are in the chip joint undertaking consortia. Sometimes those are the big corporates that you want to tackle. So we also try to do this liaison. In the other portfolio, I'm having a lot of discussions on IP and on licensing, and we have the privilege of having the EPO. I think Danos mentioned that. Having the EPO, for example, in that case, they are doing this landscaping of the IP for the portfolio, and it's very interesting for them because they see where they can position themselves in this IP landscaping. So I hope that we can do something similar also here. And finally, in relation to communication and dissemination, of course, all these activities that we do in common, and we put you in contact with all the stakeholders, common workshops, even organizing some conferences. So this is also something that is being done on a regular basis also. So just I think this is just as mentioned at the beginning. So various strategies have been tested, but still there's much room to improve power consumption towards near fundamental limits through the co-design of the geometry, the materials, the circuits, the integration in a holistic approach. And we really want to change these energy consumption projections and find a way to really reduce what's happening to our planet. So this is mainly the content. There are a couple of specific conditions in this call. One of them is that you should be proposing some kind of metrics for the technologies and also some methodologies to measure them and to establish some benchmarks. We are also working on that, and we will help you in that, but we would like to see what you propose as metrics and how you want to benchmark your solutions, your technological solutions. And of course, we don't want to do this by using toxic materials or using really critical raw materials. So please be careful and don't projects that will be using those will not be selected because they would not be in line with what we're expecting. And well, the expected project size, you know that the maximum expected is 4 millions. I think in this case, it will be mostly for millions because I think those are challenging, very expensive research. And so I think it will be around 4 millions. The indicative budget, Bart mentioned, it's around 24 million euros. This is what we are expecting. And this is what I wanted because I really wanted to leave it open for discussion and for your questions. And then we will have some time for the pitching and your interest in collaboration.